Picture the moment a cold piece of steak hits a screaming hot pan. You hear the sizzle of evaporating water, you watch the fat render, and you wait for a thick, brown crust to form. We do this because of a specific instruction written in 1847 by a German chemist named Justus von Liebig. Sitting in his laboratory in Gießen, von Liebig observed meat cooking and scribbled down a guess. He pictured raw meat like a saturated sponge. By applying intense heat quickly, he reasoned, the sponge would contract, and a hard, fast crust would act as a structural cage. He assumed the crust was a wall that prevented internal water from escaping. He ran no experiments to verify this. He measured no water loss. Yet that single unverified observation became a standard rule of modern cooking. It is the reason cooking shows tell you to sear hard, and why millions of home cooks blast their pans to lock the juices inside. The problem is, building a crust to seal in water assumes a mechanical barrier that meat tissue cannot create. We have spent nearly 2 centuries adhering to a technique that does not perform the function we assign to it. The easiest way to dismantle von Liebig's model is with a Kitchn scale, which is exactly what food writer Harold McGee did in 1990. McGee designed a straightforward test. He took 2 identical pieces of meat. One was seared hard in a skillet and finished in an oven. The other was baked completely from start to finish, with no sear and no crust. Both were cooked to the exact same internal temperature. This visualization tracks the water loss of both cuts. The seared piece lost identical water weight to the unseared piece. As internal pressure rises, water vapor pushes outward. The browned protein offers 0 structural resistance. Steam passes right through the crispy edge. The crust is not acting as a physical barrier. Searing meat does not seal in moisture. Instead, the intense application of heat triggers a chemical reaction that governs flavor, completely separate from water retention. To understand why meat actually loses moisture, we have to look inside the tissue. A raw cut of beef is composed of roughly 75% water by weight. That water is held within long, microscopic protein structures called myofibrils. Picture these proteins as coiled springs, cradling hydrated molecules between their relaxed folds. When you place meat in a hot pan, thermal energy transfers into the tissue. The internal reaction begins when the core temperature reaches 40 degrees Celsius. At 40 degrees, the added kinetic energy causes these protein springs to vibrate and unwind, disturbing the water they hold. By the time the internal temperature hits 60 degrees Celsius, the myofibrils reach their structural limit. The springs entirely collapse and squeeze together. This collapse exerts mechanical pressure on the water molecules. The tissue forcefully ejects the liquid, similar to a fist wringing out a wet towel. This process is universal. Protein contraction ejects water, regardless of whether the exterior of the meat is pale and steamed or seared dark. Heat denatures the protein. Once those structural folds unfold, the tissue loses the physical capacity to hold the volume of water it retained when raw. Moisture loss is governed by internal thermodynamics and protein structure. The exterior crust is merely a bystander reacting to the pan, not the controller of internal juiciness. We sear meat for a different biological reason. The mechanism was documented by the French doctor Camille Maillard in 1912 during his research into how the human body synthesizes proteins. This equation maps the sequence. A reducing sugar encounters an amino acid. Heated, they form a glycosalamine. In stage 2, it rearranges into an amidori product. In stage 3, these fracture into hundreds of aromatic compounds, pyrazines, furans for sweetness, thiophene for meatiness. This is distinct from caramelization. Caramelization requires only sugars, independent of amino acids, and activates at a higher threshold of 160 degrees Celsius. Maillard requires both structural building blocks. The velocity of this chemical cascade is rapid. A steak hitting cast iron generates over 1,000 new flavor compounds in fewer than 30 seconds. Nobel laureate Jean-Marie Len noted this specific sequence is the most widely practiced chemical reaction on Earth. It is the process responsible for the aroma of roasted coffee, the crust of baked bread, and the edges of fried onions. Searing is an act of engineering. You are applying controlled heat to manufacture a highly concentrated 2 mm thick layer of chemical complexity on the exterior of your food. This graph illustrates the environmental requirements. The Maillard cascade operates between 140 and 165 degrees Celsius. The plateau represents water, capping the exterior temperature at 100 degrees. Incoming energy must first evaporate the surface water before the temperature climbs into the Maillard window. Patting a raw steak with a paper towel is a mandatory physical prerequisite. It removes the moisture barrier, allowing the meat to bypass the 100-degree cap and enter the necessary thermal range. This highlights a central irony in von Liebig's guess. The evaporation of water, the exact process he tried to prevent, is the mechanical trigger required for searing to occur. Water must leave the meat for the Maillard reaction to begin. This graphic demonstrates manipulating cascade speed using surface pH. Raw meat sits at an acidic pH of 5.8. Applying baking soda creates an alkaline condition closer to 8.0. This forces amino groups to shed a proton, increasing reactivity and shortening browning time. The second chemical lever is water activity, or AW. The initial condensation stage requires a minute presence of water, but excess liquid stops the reaction. The cascade hits its maximum velocity at a water activity level of 0.6 to 0.7. Purely dry meat fails to react, and wet meat steams. Blotting the exterior with a paper towel achieves this exact numerical sweet spot. Preparing meat for the pan is an act of chemical tuning. You manipulate pH and water activity to guarantee the perfect reaction. This leaves us with a lingering paradox. If a seared steak and a baked steak both lose the exact same volume of water during cooking, why does the seared meat taste juicier when you eat it? Part of the answer lies in the thermal gradient. Intense, rapid searing exposes the exterior to high energy, but limits the duration of the cook. This protects the internal core, preventing the deep tissue from reaching temperatures high enough to squeeze out all of its water. The more powerful variable happens inside your head. Human perception of juiciness relies on a neurological calculation rather than a straightforward measurement of liquid volume. This diagram traces how the brain processes these inputs. When you take a bite, your tongue registers salt and fat, while your olfactory receptors process the Maillard aromatic compounds from the back of your throat. The brain aggregates these signals into a single neurological output labeled as juiciness. A piece of meat packed with aromatic compounds leads the brain to perceive moisture. In contrast, a physically wet but chemically bland piece of boiled meat registers neurologically as dry. The Maillard reaction manufactures the physical sensation of moisture. The thousands of newly formed flavor molecules dictate the reality your brain perceives. We can apply this chemical understanding to improve technique in the kitchen. The reverse sear method is engineered around these specific thermodynamic rules. The first step is thermal control. By cooking the meat slowly in a low-temperature oven, you gradually bring the internal core to its target, avoiding the protein collapse that would otherwise force water out. Step 2 triggers the chemistry. You place the fully cooked, dried exterior into a blisteringly hot pan for 60 seconds, crossing the 140-degree threshold to fire the Maillard cascade. This sequence decouples the two mechanics of cooking meat. You maintain the structural integrity of the internal proteins while independently maximizing the external flavor chemistry. The 1847 model is obsolete. We sear to ignite the Maillard reaction. We pat meat dry to satisfy the physical requirements of phase change. We build crusts for flavor, not for cages. The next time you cook, treat your pan as a precision instrument. Test the reverse sear. Manipulate your variables, and run your own experiments. Hit subscribe for more food science deconstructions, and I will see you in the next breakdown.